In this unit, we will discuss the psychological roots of innumeracy. Innumeracy is the title of John Paulus' influential book. Paulus argues that a citizen's inability to deal with numbers results in misinformed governmental policies, emotional risk assessment, confused personal decisions, and an increased susceptibility to pseudoscience. However, to our students and the general public, it seems that a great majority of people manage to function fine in our society without ever using the numerical and algebraic skills they've learned in school. Some successful people even proudly declare their weakness in mathematics. The purpose of this unit is to understand the interaction and conflict between intuitive and analytical thinking. Every day, we make hundreds of decisions, and most of the time, we're not even aware of it. Human intuition is so remarkable that no computer comes close to matching it. However, psychological studies have found that people systematically make unconscious errors of reasoning that distort their judgment. Understanding the psychological causes of the human brain's struggle for storing and processing numerical information is a useful first step to helping students overcome their quantitative blind spot. Ultimately, students can use this knowledge to better predict when their brain is a source of reliable information and when it's likely to mislead them. Intuition is essential for us to function in everyday life, yet we don't notice it unless it's missing. Let's take vision as an example. We don't go to school to learn how to recognize faces or visually estimate distance, but when we think about it, isn't it amazing that people can navigate a crowded subway station without bumping into each other? Consider this baseball player catching a ball, which is flying in a parabolic trajectory. We can almost be sure that his training does not involve solving quadratic equations, but it is too naive to conclude that school mathematics is not useful or necessary. Intuition works extremely well in a routine and typical situation. But we cannot rely on our intuition to solve problems that are not grounded in the immediate here and now, or make a decision that might have a significant impact. To see how easily our own eyes can be deceived, take a look at this picture. The bottom line appears to be longer. But if you've already encountered this image, you recognize it as the famous Mueller-Lyer illusion. The horizontal lines are in fact identical in length. Here's another example, created by the cognitive scientist Roger Shepard. The surfaces of the two tables have the exact same shape and area. Vision is not the only domain of illusions. Illusions of thoughts are called cognitive illusions. In 1974, Amos Tversky and Daniel Kahneman published a seminal paper in Science entitled Judgment Under Uncertainty, Heuristics and Biases, in which they documented many biases and misconceptions when people make intuitive predictions and judgments. Many of the cognitive illusions involve numbers and probability. Professor Kahneman won the 2002 Nobel Prize in Economic Sciences, which is quite an unusual feat for a psychologist. In his recent book, Thinking, Fast and Slow, he summarized his life's achievements. The overarching conceptual framework of discussion is the dual process theories of human thinking. System 1 relies upon frugal heuristics yielding intuitive responses, while System 2 relies upon deliberative analytic processing. Crudely, we can regard System 1 as intuition and System 2 as deliberation. To observe, your mind is in automatic mode. Let's say 2 plus 2. The answer comes to your mind immediately and intuitively. This is an instance of System 1 thinking. Now look at this problem. 17 times 24. Probably nothing comes to your mind. You have to generate the solution, but you have to decide to do so first. System 2 allocates attention to the intense mental activities that demand it, including complex computations. Carefully read some examples of activities that are attributed to System 1 and System 2. Can you identify one feature in common for the highly diversive operations of System 2? You can pause this video to allow yourself more time. The highly diverse operations of System 2, or deliberative thinking, have one feature in common. They require attention and are disrupted when attention is drawn away. You could not compute the product of 17 times 24 while making a left turn into dense traffic, and you certainly should not try to. Quantitative reasoning requires activation of System 2, deliberative thinking, which requires effort and does not come automatically. It is no wonder that quantitative reasoning is challenging for untrained students and citizens. Some of you might wonder if deliberative thinking is so important. Can't we just ask students to pay attention to every single detail? The answer is no. We live our lives continuously and vigilant and is simply not practical. In fact, intense focusing on a task can make people effectively blind. There is a famous invisible gorilla demonstration. If you're not familiar with this study, we invite you to participate in a simple experiment later in this unit. Our brain works hard to help us survive and accomplish our goals in a complicated world. We often have to react quickly to emergencies and opportunities, and our fast-thinking system is in charge most of the time. Only when our fast-thinking system runs into difficulty does it call on the slower-thinking system to support the more detailed and specific processing. The division of labor between System 1 and System 2 is highly efficient, as it minimizes effort and optimizes performance. However, it can lead to predictable mistakes. Let us consider this example. When people are asked how much it would pay for an insurance policy that would pay $100,000 in case of death for any reason, and a policy that would pay $100,000 for death because of terrorism, people decide to pay more for the second, even though it's far less likely to die of terrorism than any other form of accident. Later in this unit, we will see more cases in which decisions are based on automatic response and distorted beliefs concerning the probability and size of potential loss. We hope by now that you have a better understanding of how the mind works and why some students' mistakes are so common. With this understanding, we should not be too harsh when students did not reason quantitatively. Instead, we can use the opportunity to deliver the bottom line message to them. Quantitative reasoning requires effort, and attention must be paid.